Well, I was, we have been invited to present at Dublin, the Dublin workshop. However, the paper was rejected and I was very disappointed. The reviewers were technically wrong and missed several points. So I'm going to go present and, basically show them where they were wrong. I'm also going to write to the conference chairs. I'm just really getting tired of the level of engagement. Um, but I also used the energy of my disappointment to implement. I'm moving towards an automatic formal verification of the results. So I went ahead and spent a couple of hours and implemented just a REPL for the row combinators. I'll give a quick demo here. I have to jump off early today, but I did want to give a quick demo. So here we go.
Yeah, this is very disappointing for the paper.
Yeah, it is, but we were still invited to present, so I'll present.
I'm definitely glad for that.
Okay, so anyway, so here, let me just quickly walk through the code. So I took the time to. Part of the reason I'm doing this is because I'm investigating Kiyama as a system for expressing rewrite systems in Scala. That's its goal. And since I need a rewrite system input format in order to express ladle, that's why I did this work. So here's the project. It's also up on GitHub. I made it a public repo. And if we dive down, so I haven't automated the construction of the BNFC like it is in Rolang. So I built the BNFC and then generated the Java by hand and then moved it over into a Java directory. So I'll automate that later. It just wasn't super important to me. But here's the grammar. It's teeny tiny. Basically we've got, combinators. I mean, it matches the paper exactly, right? So we've got 0, the message combinator, the kill combinator, the duplicate combinator, the sequence combinator, the forwarding combinator, the branch left, branch right combinators. And then we also have processes which are dereferences of names and parallel composition, and names are quoted processes. That's it, right? Nothing, I mean, just matches the paper exactly. And then I use that to generate both the Java source and the make file, and then move the Java source over into the Java directory. And then here's the code, the source code that I've got so far. Essentially, because BNFC does not have a Scala target, I have to make case classes. Like if this were a large scale language, I'd think long and hard about possibly writing a Scala backend for BNFC, but because it's so tiny, it doesn't matter. So I've got, essentially I've mimicked the expected output of BNFC if it were, if it had a Scala backend, so that this can be used by Kiyama. Kiyama requires that they be case classes. You can't use other things. And those other things are the output of the BNFC. So again, it's exactly as you expect. The non-terminals are traits, and then we've got a case object for the 0, and then because it has no parameters, and then we have a message, a do, kill, et cetera, right? And then there's the dereference and the par, and then a name is a quoted process. So exactly as before, just mimicked in case classes. And then in the optimizer, we have this, basically when I get an AST from the BNFC style parser, I just convert it, right? So that's all that's happening here. What I will do is do what Kyle does, which is to make a normalized form. So I will add an ordering on processes that's based on their complexity. So I'll add that ordering, and then we'll get a normalized expression. Right now it's just it produces just a mirror of the syntax tree, but when I just have to write down the order, and which is obvious. It's very straightforward to come up with an order in this case, and then this will do a little bit more than just mirror or reflect the syntax tree over into the other form.
And this ordering you need for equivalence, or
yeah, for the ordering you need for fast equivalence check.
Okay.
Right. I mean, we could do an easy equivalence check, but for fast equivalence check you need an ordering. And then there's a pretty printer for so you'll see that in a second, and then the evaluator. So like, because I don't have the ordering, I have to duplicate a bunch of things, right? So so in particular, if we have just singletons, right, just a single combinator, they just sit there, they don't go anywhere, right? So a message goes to a message, right? A duplicator goes to duplicator, etc. But if I have a duplicator in parallel with a message, and the subjects of the combinators match, then they do reduce according to the rewrite rules. So we'll just do one of those, right? So if I have a duplicator with a message and the subject of the two combinators is the same, then what duplicator does is it duplicates the payload of the message onto the B channel and the C channel. So you produce a new message that had with B as the subject and the same payload, in parallel with a message with C as the subject and the same payload, right? So that's exactly what happens, right? So we've got a duplicator here, A, B, and C, message MA and MP, MP for payload. And then if A is MA, right, that's this check here, right? Then we make a par expression, so that's the vertical bar, and with B and the payload, so this is message expression with B and the payload, and message expression with C and the payload. So this piece of code here matches exactly this rule. Of course, this rule is up to structural equivalence, right? So if you have so par is commutative, so you'd have the same rule if you swap these around. Since I don't have the order, I need to go ahead and put in the commutative case as well, and that's what this is doing. And then so basically there's a case for every single one of these rules here, and it's duplicated and each one is, so there's twice as many because I don't have the structural equivalence. When I get the normalizing thing going on, I can get rid of these rules. These extra rules. So that's the implementation. You can, you know, see that it all, and then there's another kind of thing, which is this is only a stopgap right here. Basically, this reduces as much on the left of a par before proceeding to the right of a par. So that's a reduction strategy, and we don't really want to be committed to such a reduction strategy. I just put it in as a you know, a stopgap, right? There are better reduction strategies, and in fact, such reduction strategies are not as efficient as the kind of execution mechanism with the hash map that we use in Rowline, right? But this is really just to do just to test out the rewrite system for Kiyama. So just something to be aware of. So that's the evaluator, optimizer, pretty printer. Obviously, the syntax analyzer is just, you know, it doesn't do anything other than hand over work to the BNFC generated thing. So then what the main thing does is so they have a thing called parsing REPL. And so the main application extends that parsing REPL, and you override process, and in this case I also needed to override process line. So I started with a template, a Kiyama template that just evaluated arithmetic expressions. So that's why there's a bunch of arithmetic expression stuff sprinkled in, and I didn't want to completely remove it until I had my, you know, a grasp of how everything worked. So that's still in there, and I might even, you know, show that you can nicely extend this with numbers, in which case keeping it around is useful. But essentially, we check to see if we do in fact have a process expression, and if we do, we just emit the pretty print of the reduce of the process, and the process line is just to wire in our parser, right? So the first thing we do is check to see if it's a process expression, and if it is, then we go ahead and process using the normalized process of. So this will parse it using the BNFC parser. If that parsing fails, then we attempt to parse it as an arithmetic expression, and if that fails, then we bail. So that's a quick walkthrough of the code, and then you know, just to see how it runs. So if I do an SBT run, well, I'll start from fresh. So if I do SBT clean, compile, run. And so there you have it. So I can, for example, take this expression here, which is a self-contained process expression, right? So it's listening on the channel at the kill expression is listening on the channel at 0. The message sends a payload of at 0 on the channel at 0. And so we expect this to just reduce to 0, right? That's the equivalent of this thing here, just instantiated with the name at 0. And reduce it to 0. So let's try something fancier. So let's do duplicate. So if I do duplicate, so the subject is at 0. And now I'll do at message at 0, comma uh, at 0. So that's one channel, and I'll do at kill at 0. So that's another channel, right? So every channel is a quoted process, right? So well, let's see what happens. I haven't tried this one. Oh, looks like it worked, right? So we duplicate the payload. So here's the duplicated payload. There's that, and the first payload is sitting at the channel at message, blah, blah, blah. And the second one is sitting at the channel at K. So that worked. So you're free to play around with it. As I said, this is really just input into an automated formal verification of the results in the paper. So people can see that in fact it does work. But you can certainly play around with it. And
cool.
Yeah. And it'll sort of let people eat crow. Any questions?
So I'm not completely sure that I understand what is the role of Kiyama. You have everything, right? So
Kiyama is what allowed me to. So if you go here, sorry. Okay, so if you go here, Kiyama is basically the support for this thing. This thing is special, right? It gives me a format for writing down rewrite systems, rewrite rules, right? So this is not a legal Scala expression. Yeah.
So this is like a compiler extension.
Yeah, that's right. Kiyama basically provides a little mini language for writing down rewrite systems.
Oh, I see. Oh,
yeah.
I see.
So what Ladle needs as an input, Ladle needs two things, right? It needs, let me split the screen. Okay, and then go to the AST. Okay, so Ladle needs the Levere theory, which is basically this part, right? The Levere theory for the notion of computation is basically going to be a grammar, right? That's what the Levere theory, that's the role of the Levere theory. Let me expand this so we don't have line red. Almost, let's try it from the other side. Oh, well, still gonna have it, but all right. Anyway, so so Ladle needs this, and it also needs a format for expressing the rewrites. So that's this part. So Kiyama basically has all the ingredients to specify the input to Ladle.
I see.
Yeah. So
that's it can be done without, but it's much more code, right? Because
a lot more
you need
code.
to do this.
Yeah.
Okay.
Yeah, exactly. It's a lot more. It's a lot more code, and Kiyama, the important thing is that Ladle needs an internal representation to go and do the calculation. Right, and so it needs to take this data that's on the screen here, or data that's like this, not exactly this data, but data that's like this, and then manipulate that data. So it's going to produce a new set of case classes, right? So the new set of case classes. Let me find it here. There it is. So the new set of case classes will basically be given by this, right? So we'll have the notion of context. We'll have the notion of uh, uh, yeah, so all of this is making contexts. And then we'll have notions of lambdas. So these are linear lambdas. And then we'll have a notion of application, right? So we'll have context, linear lambdas, application, a resource context, a par, and a cup, and yeah, and those will be the extra case classes that we add to this set of case classes.
Oh, I see.
Right?
So, so we are doing calculation with this extended AST.
That's right. So
And then
we're gonna take one of here to walk it through carefully. All right. So we start with an AST like this, right? So
this is our source language that we want
this
to.
is our source language, exactly. And then we're gonna we modify it in stages. I just cut to the chase. So the first thing we do is we add the resourcing. So we have a case class for R, we have a case class for par, and a case class for cup. So those are the three kinds of case classes we add, and then we add contexts. So that's these operations here, and linear lambdas and application. Right. So that's the total set of things, case classes we're going to add to these. And then we're going to change the rewrite rules, right? So the rewrite rules are going to be resourced, right? So you don't get to rewrite unless you have an R around your redx. Okay, and then there's a similar kind of thing that has to do with context, but I won't go into that. And then once you have that, then we can then these are the types that will be automatically generated. And so you'll have structural types for every one of these guys. That's this K bit. And then you'll have structural types for all those case classes that we've generated. And then you'll also have these rely, guarantee, arrow types and collection types. So all of that will be automatically generated. And then these are the typing rules, right? So if you give us an expression, if you assert a particular type of an expression, we'll be able to determine whether or not the expression types that way. And expressions that are well typed will always enjoy the properties that are expressed by the type. And we also no longer have to have persistent properties. We were able to get rid of that constraint. So the properties are basically anything expressible in the type system. So the type, go ahead.
Can you say, what does it mean persistent properties?
Persistent properties are things that strongly normalizing is persistent in the sense that anything in par with 0 is that thing.
I see.
Right, or anything P in par with bang P is the same as bang P.
I see.
It has to do with its relationship to the K combinator. But we've removed that. We've removed that restriction. So it's that part is no longer. So anything you can express with the types, you can express, and the types are incredibly rich, right? So almost certainly the types are not even decidable. So you have to pick a subset because of the right triangle and the par structure. Almost certainly this is so rich that it's not decidable. So you pick a subset of these types to get decidable properties, and or you pick a subset of the terms, right? Which is totally normal, right? Like chi-race picks out a very intriguing set of processes for which his logic is decidable, and because it's non-trivial and it's interesting. It's an interesting set of processes. So I don't even know what its expressive power is. Um,
And on which level we need to decide to choose this subtype?
so basically, you can, if you're talking with people, you can use the entire type system, right? And like if you know what you're doing, you can go and use the rules by hand. But if you want to automate that process, then you're going to have to limit the rules. But the nice thing is that we have, at least in the case of the row combinators and the SKI combinators, we have a stratification mechanism, right? So we can talk, precise, like the row combinator. What the row combinators do for us is they say, this is it. This is all you've got to make all computation ever. So if you want to stratify your computation, what do? Well, you can leave this one out and just use these. Or you can keep that one and leave this one out and just use the rest, et cetera, right? So you can now build, and there's another trick that you can use with row that you can't. So I just described basically the separation techniques used by Yoshida in her combinator paper. There's another technique that can be used in row that isn't available in Yoshida combinators, which is you can limit the kinds of names that can be sent in a message. So you can limit the payloads, and that gives you another stratification technique. In fact, in general, I mean, this is probably the first time ever I'll say it in public. One of my aims with the row calculus was to provide a framework in which to go after a much better complexity theory for computation. And here's the reasoning and rationale behind the design. Let me see if I can find the paper. A second. All right. Well, anyway, if you look at the row calculus paper, what you'll see is, oh, I've got it at the bottom here. Yeah, sorry, I forgot. It's in the appendix. Okay, there we go. So here's the row calculus paper. All right, very tiny calculus. So the point is that you could limit the kinds of names that you're allowed to send by limiting the kinds of processes that can occur here. And in this way, you can stratify this calculus in terms of expressive power. So if you think about the normal complexity hierarchy, right? So regular, context-free, finite machines with one pushdown store, finite machines with two pushdown stores, which is the same as Turing machines. So the issue is every time you change expressive level, you change the formalism dramatically. Right. So from regular to context free, you have a pretty dramatic shift in the format. Now here, because you have this ability to stratify by restricting what you can put in the payload part of an output, you can create levels of expressive power. So you can build a restriction which gives you the equivalence of regular. You can build a restriction which gives you the equivalence of context-free, and so on. And so the point of this is that you have this uniform framework in which to investigate expressive power. And my hope had always been that providing a uniform framework in which to investigate complexity, you could go after P equals NP, right? The issue is every time you change complexity levels, you change the formalism so much that it changes the shape of the arguments. Here, we don't change the formalism at all. We're just tweaking, what goes in one position. That's it. That's all. And so it felt like it might be a better framework in which to tackle the P equals NP problem.
Nice.
So I mentioned that in the context of the other Yoshida result. So rho gives you a different stratification technique than just leaving out the combinators. Anyway, so that gives you this ability to stratify computation, and because you can sort of in a much more rigorous and deterministic way stratify the computation, you can relatively easily find subsets that have decidable typing. So that's the point of that. Okay. Any questions quickly, because I do have to jump off now.
Yeah, thanks for this explanation. Yeah, it totally makes sense, and yeah, very helpful for me.
No, thank you for your questions. Please play with the code if you have a spare moment. It's
yeah,
and it's that's I mean it's just a toy, but it hopefully once I get it to slightly better shape, it will make a point in Dublin.
Yeah. So I was thinking that maybe I can present here in Zagreb. How can someone learn multiple languages just understanding this general principle of computation?
Oh yeah, that's a great idea.
Because all languages are using rewrite rules, and they're very similar. So yeah, I was thinking that maybe understanding this general principle someone can more easily understand many languages.
I think you're absolutely right. I mean that's been our hope is that because there's not a lot of uniformity in the computer science community, right? Even though behind the scenes there is a lot of uniformity, right? If you look at the specification of the JVM, it's really a rewrite system, but they don't think of it as a rewrite system. Right? They think of it as transition rules with respect to a machine. But those transition rules are in fact a rewrite system. It's just what you're rewriting is bigger than the expressions in the language. It also includes the machine state. And once you see that, then you start to understand the difference in certain kinds of language designs, right? So there's a language like Java where looking at the code, you cannot see everything that's going on, because you have to, in your mind, keep a model of the machine state as you're simulating code. Whereas in the lambda calculus, everything is there. There's no extra machine state. All of it is in the term. And in the pi calculus and the rho calculus and the rho combinators, all of those, everything is in the term. There's no extra machine state you have to keep in the back of your mind, which is very important when we think about not only programmers understanding their own code, but static analysis of code. Static analysis of code that that cannot be understood without machine state can't work. You have to include the machine state. static analysis of code that does include all the state right in the code, that has a better shot, right? You don't have to, there's just not this hidden stuff you have to model. So all those are really specific practical points that come to the fore once you start asking about, you know, what's common to all of these things. All right, I got to jump off, but thank you guys. I really appreciate your time and attention.
Thank you.
Great. Thanks, Greg.
And thank you, Christian, for facilitating this.